In the previous lecture, we have started to deal with the problem of calculation of carrier concentration and Fermi level for intrinsic semiconductor. And in the first part of the lecture on this subject, we have calculated only the carrier concentrations in intrinsic semiconductors. When you say carrier concentration, that means we have calculated the concentration of electrons in conduction band and the concentration of holes in valence band. And we have denoted the concentration of electron in conduction band by the symbol Ne, and we have obtained the result that Ne is equal to Nc times exponential raised to the power minus Ec minus Ef over Kt. And the expression for NH we have obtained, that was given by Nv times exponential raised to the power minus Ef minus Eb over Kt. Actually here this number Nc, what is this Nc? You have learned that this Nc is called the effective density of states of electrons at the conduction band edge, and this Nv is known as the effective density of states of holes at the valence band edge. Okay, and the expression for Nc and Nv you can see here, which we have learned in the previous lecture. Okay, here you know this Ec and Ev are what? Actually, Ec denotes the energy level of the bottom of the conduction band, and Ev represents the energy level of the top level of the valence band. Okay, and actually the Fermi level of this intrinsic semiconductor lies between this Ec and Ev, which I have denoted by the symbol Ef. And in this present lecture, our aim is to find what will be this Ef, that is what will be the Fermi energy or Fermi level, particularly in case of intrinsic semiconductor. Although the expression which we will obtain, that will be actually valid for the case of extrinsic semiconductor too, after some modification, which we will learn in our forthcoming lectures. Okay, and you know this Ec minus Ev, this is actually called the energy band gap, which we denote by the symbol Eg. You can see. Okay, and in this lecture we will also learn about the carrier concentration in terms of Eg2. Okay, so starting from the results which we have obtained in our first lecture on this subject, we will calculate the Fermi level of the intrinsic semiconductor. This is our prime aim, but along with it we will also learn about a very important concept which is called law of mass action in this lecture. Okay, so now let us see how we can obtain the result for Ef in case of intrinsic semiconductor. Although the results which you have written here and obtained in previous lecture for the concentration of electron and holes, you know these two results also hold for the extrinsic semiconductor. Although we have obtained it for intrinsic semiconductor, but these results also hold for extrinsic semiconductor. Okay, and if your aim is to write these expressions for particularly for intrinsic semiconductor, we will do some modification. Actually, if your aim is to express these two results only for intrinsic semiconductor, then you have to use a new term EI, which is actually called intrinsic energy level. And this intrinsic energy level is nothing, this is simply the Fermi level in case of intrinsic semiconductor. Because we want to differentiate this result for the extrinsic and intrinsic semiconductor, so for indicating that these results we are using only for intrinsic semiconductor, we will replace this EF by EI, so that our result will indicate that we are talking about the intrinsic semiconductor. Okay, and at the same time, this Ne, which represents the concentration of electrons in conduction band, we will now use the symbol Ni. Okay, and for Nh, which represents the concentration of holes in valence band, we will now use the symbol Pi. So actually this subscript I is used for the intrinsic semiconductor. Okay, so you can see that result in terms of this EI instead of EF can be written like this. This Ne is now written as Ni, and that will be given by Nc times exponential raised to the power minus Ec minus Ei over Kt. You can see here this EF has been replaced by Ei. Okay, only to indicate that this result now we are going to use only for intrinsic semiconductor. Okay, and Nh, which will be now written as Pi, that is given as Nv times exponential raised to the power minus Ei minus Ev over Kt. You can also see here that this EF, which was originally present here, that has been replaced by Ei. Okay, but you have learnt in our previous lectures that in case of intrinsic semiconductors, the concentration of electron in conduction band and concentration of holes in valence band, both are always equal. So since Ne is equal to Nh, so now we will use a symbol Ni for the carrier concentration. When you write Ni, that represents the carrier concentration in case of intrinsic semiconductor, and that will represent the concentration of both electrons and holes. So we will now use the symbol Ni for both. Okay, but since Ne and Nh are equal, and Ne and Nh you give by these expressions, so for getting the expression for EF, now equate these two values. So you can see this is the expression for Ne and this is the expression for Nh, and both are equal in case of intrinsic semiconductor. So I have equated these two expressions. Okay, now simplifying this result, our aim is to find the expression for EF or Ei. Okay, and for this you can see I have simplified it. This can be written as exponential raised to the power minus Ec minus Ef over Kt divided by exponential raised to the power minus Ef minus Ev over Kt, and that will be equal to Nv over Nc. This is a simple algebra. Okay, and so this LHS can be now written as exponential raised to the power minus Ec plus Ef plus Ef minus Ev over Kt, and that is equal to Nv by Nc. Okay, so this LHS becomes exponential raised to the power 2Ef minus Ec minus Ev whole divided by Kt, and that is equal to Nv over Nc. Okay, so from the definition of logarithm, you can write that this power of exponential, that is 2 times Ef minus Ec plus Ev over Kt, that will be equal to natural log of Nv over Nc, that is ln Nv over Nc. Okay, and so this 2Ef minus Ec plus Ev, that will be equal to Kt times log of Nv over Nc, and so this 2Ef is equal to Ec plus Ev plus Kt times log Nv over Nc. Okay, and so the expression for Ef, which is also denoted by the symbol Ei in case of intrinsic semiconductor, that is given as Ec plus Ev over 2 plus Kt over 2 times log of Nv over Nc. And This is the expression for Fermi level in case of intrinsic semiconductor in terms of this effective density of states NV and NC. But the expressions for NV and NC. So using the expression for NV and NC, now we can find the value of NV over NC in terms of the effective mass of holes and electrons. NV is given by this expression, that is, this is equal to 2 times of 2 pi mh star kt over h square whole to the power 3 by 2, and that will be divided by NC, and NC is 2 times 2 pi me star kt over h square whole to the power 3 by 2. You can see, except mh star and me star in RHS, all the terms are identical, so they will cancel out, and so finally we get that the ratio of NV and NC is simply equal to mh star over me star whole to the power 3 by 2. Okay. So in the expression for this EF defined in this equation 1, now instead of this NV over NC, you can write mh star over me star whole to the power 3 by 2. So replacing this NV by NC by this value, the expression for the Fermi level, particularly in case of intrinsic semiconductor, is now given like this. This is EC plus EB over 2 plus KT over 2 log mh star over me star whole to the power 3 by 2. But from the properties of logarithm, that log a to the power n is equal to n times log a. So using this property, this second term can be written like this. This 3 by 2 will be in the multiplicative factor, and so EF can be written as EC plus EB over 2 plus 3 over 4 times KT times log mh star over me star. So this is our final expression for the Fermi level in case of intrinsic semiconductor. Okay, and you can see the value of this EF, which is Fermi level or Fermi energy for intrinsic semiconductor, depends on this temperature T. Okay, and apart from that, it also depends on the effective mass of electrons and the holes in this semiconductor. Okay, so if you will take the temperature at 0 Kelvin, that is at absolute 0, then this second term will vanish. Okay, when you will take t equal to 0, you can see that since t is 0, so this second term will become 0, and in that condition, what will be this EF? EF will be simply equal to the first term, that is EC plus EB over 2. Okay, so at 0 Kelvin temperature or at absolute 0, the Fermi level of an intrinsic semiconductor is given as EC plus EB over 2. And what this result shows? You can see, since at absolute 0 temperature, Fermi level is simply EC plus EB divided by 2, it means at T equal to 0 Kelvin, this EF is equal to EC plus EB over 2. It means this Fermi level lies just in the midway of the conduction band and the valence band of this intrinsic semiconductor. Okay, but this fact is true as long as we are talking about the absolute 0 temperature. So particularly at absolute 0 temperature, you can say the Fermi level lies in the midway between the bottom of the conduction band and the top of the valence band of this intrinsic semiconductor. Okay, but if T is not 0 Kelvin, you can see if temperature T is not 0 Kelvin, then what will happen? Then this Fermi level EF will lie to some extent on the temperature. But if we consider that even when temperature is not 0 Kelvin, okay, but the effective mass of hole and the effective mass of electron, that is MH star and ME star, are equal, but T is not 0 Kelvin. T is not 0 Kelvin, but MH star is equal to ME star. Then what will happen? Since in that condition you can see natural log of MH star over ME star will be natural log of 1 and natural log of 1 is 0. So in spite of the fact that T is not equal to 0 Kelvin, if we assume that the effective mass of holes and electrons are equal, then again this second term will vanish, okay, due to the equality of MH star and ME star. And in that condition we can say that even the temperature is not 0 Kelvin, but the EF is equal to EC plus EV by 2. It means if in that condition too, the Fermi level lies just in the midway of the conduction band and the valence band. But is it true that MH star is equal to ME star? Answer is no. In fact, in general we know that effective mass of holes and electrons are not equal, because the electrons and holes move in the different physical condition in conduction band and valence band. In conduction band, you know, electrons move only under the external electric field. But in the valence band, the motion of hole is governed not only by the external electric field, but also by the field generated by the ion cores. And so that the effective mass of hole is something greater than effective mass of electron. And if MH star is greater than ME star, then this log MH star over ME star will be equal to, cannot be equal to 0, but it will be greater than 0, that is positive. And if it is positive, then you can see this due to the presence of this non-zero second term, with increase in temperature T, the Fermi level will increase, the value of EF will increase, okay. But this increment of Fermi level due to the rise in temperature is not very effective. It is not very reasonable. It is not very appreciable, because the rise in Fermi level is very small, and so that very small change in Fermi level can be neglected in any practical purpose. As for example, you can see if you are talking about the silicon semiconductor, okay, and you are taking the temperature almost equal to room temperature, that is 300 Kelvin, then it is found that the Fermi level gets raised only by 0.01 electron volt. This is a very small value. So this level, which is just let us see, if this is the Fermi level at 0 Kelvin temperature, then the Fermi level at 300 Kelvin, there will be a difference in these two levels only by 0.01 electron volt, which is negligibly small. And so for all practical purposes we can neglect it. So practically we say that the Fermi level of intrinsic semiconductor is almost independent of temperature. Not strictly independent of temperature, but almost. Because due to rise in temperature, the Fermi level changes by a very small amount, which can be neglected in practice. Okay, I think you have understand what I want to convince you. Okay. Now, after knowing the idea of Fermi level, how this Fermi level depends on temperature, and why we can neglect its temperature dependence. Now it is time to know a very important law which is called law of mass action. And in this heading, we will also learn about the intrinsic carrier concentration in terms of the band gap Eg. Okay, that is a very important result. Okay. So to know about this law of mass action, we will start to the fact that in case of intrinsic semiconductor, the concentration of electron Ne in conduction band and concentration of holes in valence band both are equal. And we have denoted these two by the symbol Ni, which is called intrinsic carrier concentration. Okay. So if you will take the product of these two concentrations, that is Ne times Nh, that will be simply equal to Ni square. But you have learnt that this Ne is given by Nc times exponential raised to the power minus Ec minus Ef over Kt. And Nh, this is given by Nv times exponential raised to the power minus Ef minus Eb over Kt. Okay. So this Ni square is given like this. This is Nc times Nv times exponential raised to the power minus Ec minus Ef plus Ef minus Ab over Kt. Now this minus Ef and plus Ef will cancel out. Okay. And we will substitute the values of Nc and Nv which we have defined earlier. You know, Nc is given by this expression. This is 2 times of 2 pi Me star Kt over H square whole to the power 3 by 2. And Nv, this is given by this expression. This is 2 times of 2 pi Mh star Kt over H square whole to the power 3 by 2. Okay. And this is e to the power minus Ec minus Eb over Kt. Okay. Because this Ef and Ef has been cancelled out. But what is this Ec minus Ev? You know, this Ec minus Ev I have shown earlier. This is simply equal to Eg, which is called band gap. Okay. So this Ni square now can be written as 4 times of 2 pi Kt over H square whole to the power 3 by 2. Okay. And this 2 and 2 will cancel out. And times Me star times Mh star whole to the power 3 by 2 and times exponential raised to the power minus Eg over Kt. Okay. And so finally you can write that this Ni square is equal to 4 times 2 pi Kt over H square whole to the power 3 by 2 Me star times Mh star whole to the power 3 by 2. Okay. Whole to the power 3 by 2 and times exponential raised to the power minus Eg over Kt. Okay. Now you know this is the expression for a square of the carrier intrinsic carrier concentration. And from this result you can see that in case of a particular given semiconductor, this Eg is constant. This Eg will be different for different intrinsic semiconductor, but for a particular semiconductor it will have a particular value. As you have learned earlier that at room temperature for Si, this Eg is equal to 1.1 electron volt, and at same temperature, that is at same room temperature, the value of Eg for germanium is equal to 0.73 electron volt. So for different semiconductor, although it will be different, but for a given semiconductor it will be constant. Okay. And so if you consider a particular temperature T2, then at a particular temperature for a given semiconductor, this Ni square will have a particular value. It will be constant. So we can say that for a given semiconductor at a given temperature, Ni square, which is equal to Ne times Nh, that is equal to constant. And so this is actually called law of mass action. Okay. In fact, this law of mass action, which we have mentioned here for the intrinsic semiconductor, this is true not only for the intrinsic semiconductor, but it also holds for the extrinsic semiconductor. Okay. Actually, in case of extrinsic semiconductor, if the impurity atoms are added to a semiconductor to increase Ne, to increase concentration of electron, then it is found that there will be a corresponding decrease in concentration of hole. So whenever in case of extrinsic semiconductor this Ne increases, then NH decreases by the same amount or by the same times. For example, if you consider that Ne is increased 2 times, then NH will be decreased by 2 times. So the product will remain constant. And that's why we say that this law of mass action is valid not only in case of intrinsic semiconductor but also in case of extrinsic semiconductor. But there is a difference. In case of intrinsic semiconductor, you know, this Ne and NH are always equal, but in case of extrinsic semiconductor, Ne and NH are not equal. We can, whenever we add the impurity atom, definitely if the impurity atom is pentavalent, then Ne will increase, but at the same time NH will decrease in such a manner that the product will remain constant. Okay. But if you will add the trivalent impurity, then NH will increase, but Ne will decrease at the same time by same factor, and so the product will again remain constant. So this law of mass action is valid not only for intrinsic semiconductor but also for extrinsic semiconductor. Okay. Now after getting this result for Ni square, where Ni you know is called intrinsic carrier concentration, now you can find the expression for this intrinsic semiconductor, intrinsic carrier concentration in terms of the band gap Eg. Since Ni square is given like this, which is defined in this equation C, so you can find Ni, and for this you have to take the square root of the RHS of this equation C. So after taking the square root, we get the value of Ni, and that will be equal to 2 times 2 pi kt over h square whole to the power 3 by 2 times Me star times Mh star whole to the power 3 by 4 times exponential raised to the power minus Eg over 2 kt. Okay. Now this result can be written as Ni equal to N0 times T to the power 3 by 2 times exponential raised to the power minus Eg over 2 kt. Here actually this capital N0 I have written for this expression. Okay. And so you can see from this result that with this band gap Eg, the concentration Ni decreases exponentially. So if Eg is larger, Ni will be smaller, okay, at a particular temperature. And with rise in temperature T, this Ni will increase very rapidly, because here T is present in 2 factors. Here there is T to the power 3 by 2, and in exponential factor again T is present. And at both places, if T will increase, then the value of RHS will increase, and so Ni will increase. And if you are talking about a temperature T equal to 0 K, let us see what will be Ni. When T is 0, then Ni will be N0 times 0, because T is 0, and times e to the power minus infinity. This is also 0. So this will be finally 0. So at 0 Kelvin temperature, you know, the carrier concentration is 0. It means there is no electron in the conduction band and no hole in the valence band. And that's why we simply say that at 0 Kelvin temperature this semiconductor behaves like an insulator because there is an absence of charge carriers. Okay. Actually, in this graph, you can see I have shown the graphical plot of Ni in against of t. And at t equal to 0, you can see the value of Ni is 0. But as the temperature is increased, Ni increases very rapidly. And our semiconductor starts to behave like a conductor because a large number of charge carriers become available to conduct the electricity. Okay. So I think you have clearly understand after this second part of the lecture how we can calculate the carrier concentration in intrinsic semiconductor, and after knowing the carrier concentration how we can find the Fermi level in case of intrinsic semiconductor. You have also learned that the Fermi level of intrinsic semiconductor is although temperature dependent, but this dependence is not very strong, and so that almost the Fermi level of intrinsic semiconductor is independent of temperature for practical purposes. Okay. So I think after this two lecture, this problem has been solved very clearly, and you will be definitely get benefit if you will watch the two videos in sequence. Okay. Thank you very much.